So we'll look at mass and weight now, and an easy way to do that is to measure using a balance. So we can, if it balances, that means that forces are equal on both sides, and if it doesn't, that means one's greater than another, a little bit like a seesaw. Now, but we get confused with mass and weight, and the reason for that is that mass is how much matter there is in something. So if you've got 2 or 3 objects, they might all have different mass. The force of gravity acts on mass, and gravity is pulling us down to the centre of the earth, and we can measure that force in newtons. Now, when we measure weight, when you jump on the weighing scales, when you measure how much flour you're putting in your cake mixture, or you go to the shops and you buy some apples, you buy them in grams and kilograms. And actually, that's the wrong unit of measurement. Grams and kilograms tell us how much mass something has, how much matter there is in an object. The weight of something is how much the force is that's acting on the mass. And so really, what should forces be measured in? Newtons. And so we get confused because we just accept that we use the wrong unit of measurement for weight. So just bear that one in mind, and that's a great thing to learn because it's one of the biggest misconceptions in science. I want you to set this up because this is nice and easy, and it's just a coat hanger, some cups and the same length of string, the same type of cup, the same length of string suspended in the same place, and that makes it a fair test. If this one was longer, it wouldn't be a fair test. It wouldn't give us a result that we could actually rely on. And so we need everything to be the same to be a fair test. I want you to select some objects around your house. There's all sorts of things you could use. You can use coins, you can use, I've got pom-poms, I've got a little tiny Super Bowl, there's some blue tie, you can use lots of different things. But the idea is you draw a table of results. You record the object, what the object is, and then you predict which one will weigh the most, which ones could you put to balance the scale. So I'm predicting that these two are the same size, so they must be the same, they must balance the scale, and that's my prediction. And in science we make predictions, I've based it on scientific evidence because they're the same size. So for me, that means that they must be equal, they must balance because my scientific evidence tells me that they're the same size. So let's test that out. Does the balance move? Not really. Does it move on that side? Let's make sure it's suspended properly. And it is slightly different. That side is slightly lower than that side. So actually they're not balanced. One has got more mass. One has got more weight than the other. Now if we had a Newton meter or a force meter, we'd be able to measure that. But we can't. So what you can do is just keep, wow. Now that's not balanced, so they are very different. But again, they're pretty much the same size. This is an easy way to make a balance, to explore. So the idea is you're making predictions based on scientific evidence, based on something that you think is right based on knowledge and not just a guess. And then you're testing it, but you're recording it. That's the important bit. So you need to record this, take it into school, email it to your teacher and just say, I've been investigating objects that are balanced or not balanced forces. Okay?